Well, welcome. Today is Thursday, January the 14th. We're here at Spain Park doing advanced level chemistry. All right, today we're going to talk about our Lewis dot structures that were assigned to be done for today. Okay, hopefully you've got those done. Now, I did say that they weren't due until tonight, but hopefully you have them. So let's get that worksheet out. Let's look at going over some of those. And I gave my last one that I had out away, so I'm just going to let you guys tell me what the compound is, and we'll go from there. So you were supposed to do 7 through 15. Okay, we're supposed to draw the Lewis dot structure, state the shape and the type of hybridization. Now, y'all had to watch on Tuesday kind of how to do all of that. You were here Monday when I kind of went over hybridization and shapes of molecules. How do we feel right now as far as your confidence in being able to do those? You feel good?
No problems.
The Lewis dot structure, shape, and hybridization?
Good.
You feel pretty good? Okay. All right, so what's number 7?
BRF3.
BRF3. So it's critical that we draw the correct Lewis dot structure because everything else is based upon that. So the first thing we do is we count total number of electrons. Bromine and fluorine are both have 7, so it's 7 times 4, there are 28 electrons. Just go bromine, fluorine, 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 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Where do the extra electrons go?
Bromine.
On the bromine. 26, 28. Now that gives me 5 pair of electrons around that central atom. So what do we call that? An expanded octet. Okay? Now, so that's my Lewis dot structure. That's part 1. What now is the AX formula on this?
AX3E2.
AX3E2. AX3, the 3 bonding atoms, 2 lone pair. It's not the total number of electrons, it's 2 pair of electrons. All right, now you will have the sheet, the kind of the cheat sheet there, but we don't, this is an expanded octet, so the hybridization is Na, not applicable. We don't worry about it. Okay, but the shape is going to be T-shaped. T-shaped. I don't think I have one of those built. Gotta find the right one. Oh, here it is, right here. I do have one. This is what it would look like being T-shaped. Okay. You have your 5 electron pair domains. 1, 2, 3, 4, 5. They're still at the points of trigonal bipyramidal, but 2 of them are lone pair. The lone pair always come out of the equatorial position on this one because there's 120 degrees versus only 90 degrees. Okay, so that ends up making it T-shaped here. We take one more off, it's going to be linear. So you just kind of have to use your Lewis dot structure, use your AX formula, and that's how you get to your shape. Okay, so what's number 8?
SF6.
SF6. Now, as soon as I see that 6, I know it's an expanded octet. Okay, the only way to get 6 things around that sulfur is with an expanded octet. So I'm just going to go 1, 2, 3, 4, 5, 6. Now I didn't count electrons. 6 times 7 is 42, plus 6 is 48 electrons. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48. So we're good. We're an expanded octet. So what's my AX formula?
AX6.
AX6. And then that's going to be octahedron. Octahedron. Okay? Y'all all have the little things right here. Why don't we build octahedron? Okay? Do you not? Grab there, Lydia, right here is the one. Okay? Find the tan one. Pardon me. Find this tan one that's got 5 holes in it. Pardon me. Find this tan one that's got 6 holes in it. Okay? So it's kind of square looking. And then just go ahead and put, you know, it doesn't matter what color you use. Use the, if you have 6 green ones, put 6 green ones around it. Just so you can see what octahedron is going to look like. Okay, now just typically that's 100% fine, do that, but we use the small ones for single bonds, the small stiff ones, and then the long ones are for double bonds. But it's gonna look like this. Notice that it's perfectly symmetrical. It doesn't matter which way you turn it, it's always gonna be the same. But why would it be called octahedron? What's octa mean? 8. It's gonna, if you were to complete this, it's gonna have 8 faces. You're gonna have a face here, a face here, a face here, face here above, and then the exact same thing on the bottom. You know, if I was gonna name them, we have trigonal bipyramidal. I would have called this one square bipyramidal. Just the difference in the base. But they call this one octahedron because it's all symmetrical. Now, when we have a lone pair on this one, let's just say it was AX5E. Pick one, anyone. They're all 100% identical. It doesn't matter which one we're going to pick. So then we have this. So then we have what's now just, we took the bottom pyramid out. Now it's square pyramidal. Okay? Now the second lone pair though, because electrons repel one another, and lone pair electrons repel more than others because there's no positive to balance it out. So the other lone pair is going to be opposite. So this would be the second lone pair. So if it's AX4E2, it's kind of this crazy molecule, square planar. It's this flat molecule, square planar. Okay? So if the AX formula says AX4E2, square planar, but that's what it's going to look like. Just kind of give you a visual to go with the names, because some of these names are kind of weird. All right, what's the next one? Number 9.
Chlorine.
Cl2O. Okay? So it's going to look like this, chlorine, fluorine. It's going to look like that. So what's my AX formula on this one? AX2E2.
SP3.
So this, yeah, both of these are expanded octets, so we don't have any kind of hybridization on these. But this one is that a 2 plus 2 equals 4, so the type of hybridization is SP3. This is the answer. This is nothing. This is just a way to get to the answer. That's just a general formula. That's my answer. And what's the shape going to be?
Bent.
Bent. And we're going to have a bond angle. Again, the points of the tetrahedron are going to be still at, the electrons are still going to be arranged at the points of a tetrahedron. So 109.5. But what happens with lone pair and the bond angles? Anybody remember? Remember, lone pair have more electron-electron repulsion, so they swell up. They occupy more space than a bonding pair. So these are going to repel one another and force these closer together by about 2 to 3 degrees per lone pair. So bond angle in a tetrahedron is 109.5. But when it gets pushed by 2 to 3 degrees, it's going to be somewhere around 105 degrees in this bond angle. Now, it'll be different for every molecule. You don't have to know the exact, but you should know that it's less than 109.5. All right? So, number 10 is which one?
PCl5.
PCl5. So that's going to be another expanded octet because I have more than 4 things around it. So if I count my electrons, it's 35 plus 5, I have 40 electrons. Phosphorus, chlorine, 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 chlorine. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 28, 30, 32, 34, 36, 38, 40. It all works out nice and dandy. Everything's got 8. All single bonds. Enough AX formula is what?
AX5.
AX5. No hybridization on this, but the shape is going to be trigonal bipyramidal. Trigonal bipyramidal. Y'all seen this? Okay, if y'all that are watching this at home, if you have any questions, this is where you got to email me. You got to touch base or see me in class tomorrow and ask questions about it. Okay? 11. Am I still on the screen over here? Okay. So what's 11?
SF4.
SF4. Okay, so I count my electrons. 7 times 4 is 28 plus 6. I have 34 electrons. Sulfur, fluorine, 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 fluorine. Now if I go and I have 8 electrons around all 4 of these things, how many electrons total am I going to have? 8 times 4 is? 32. So I have 34, so that just kind of tells me I'm going to have an expanded octet. I'm going to have 1 extra pair. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 30, 32. So where's the extra lone pair go? On the sulfur, and it's always as a pair, just anywhere you can put it. So my formula is
AX4E.
AX4E. So we have our this one that has 1 lone pair. This is our trigonal bipyramidal, but we took 1 out of the equatorial position, so we have this. It's not really any shape. So instead we call it distorted tetrahedron because it's kind of got 4 faces, but it's all messed up. But a simpler, easier name is just seesaw. It looks like a seesaw. Okay? I see you, I saw you just up and down. That's, you know, some scientist is bored or just had a kid or something. Hey, it looks like a seesaw, like I just bought my kid. So we say the shape is seesaw. It's a lot easier to write than distorted tetrahedron. And again, it's an expanded octet, so we don't worry about hybridization. Number 12 is what?
HCN.
HCN. Okay, we had already drawn this one, I believe. It's going to look like that. Okay? So, how many sigma bonds, how many pi bonds do we have?
2 sigma bonds, 2 pi.
2 sigmas and 2 pi's, right? So what's the only type of orbital that can form a pi bond? What's the only type of orbital that can form a pi bond? This is important, you need to know that. P is exactly right. And so you have to have 2 p orbitals not hybridized. And how many p orbitals are there total? How many p orbitals on a sublevel? How many lines when we do the 1s, 2s?
3.
There's 3 p orbitals, right? X, Y, and Z. 2 of them have to stay unhybridized. So how many does that leave to hybridize?
1.
Only 1. So it's going to be SP. Now we know that this is going to be AX2. Adds up to 2, it's SP. But the reason it's SP is because we need to form these 2 pi bonds, and only p orbitals can form that pi bond. Okay? So, SP. Now, what's my shape going to be? What's it? Triple bond is always going to be the same shape, linear. Okay, it's a linear molecule, and so as a result, okay, we're going to find that that's why this is a gas at room temperature, and hopefully we're going to get into some of that today. What would the bond angle be for a line? What's this bond angle going to be? 180. 13 is what?
SEBR3 minus.
S what? P?
SEBR.
SEBR3 minus 1.
Mm-hmm.
Okay? So bromine has 7 times 3 is 21, plus 6 is 27, plus 1 is 28 electrons. Now it's real important that we get the total number of electrons. Now we just do the same thing, SC, put the bromines around it. 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24, 26, 28. So we have another AX3E2. Okay, so it's just going to be just like this one right here, BRF3. Okay, so it's going to be T-shaped and no hybridization. Bond angle is going to be 90 degrees all the way around. All right, well, let's just go and do the last two now. Is this still focused?
Mm-hmm.
14 is,
KRF4.
say that one more time.
KRF4.
KRF4. Okay, so we have 28 plus 8, we have 36 electrons. Krypton, fluorine, 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 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 4, 6, 8, 30, 32. What do I do next? Where do the last electrons go?
Krypton.
On the krypton. 2 pair, always in pair. So I have AX4E2. So that's that square planar one we were just talking about right here. AX4E2 is going to be square planar with a krypton in the middle and the 4 fluorines around it. And lastly, 15. Oh, so square planar.
BF3 is 15.
BF3. Okay? What's unique about boron being an essential atom?
Doesn't do the whole octet, it only does 6.
It only needs 6. So boron and aluminum, you just have to know that. Okay? Students miss this year after year after year because they just don't memorize boron and aluminum. So we're going to draw, we have 21 plus 3 makes 24 electrons. Boron, fluorine, 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 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Now it appears that the boron is electron deficient. Everybody wants to form a double bond with one of the fluorines because that's what we would normally do. But boron doesn't do that, and fluorine can't form double bonds. It only has 1 unpaired electrons. Halogens can only form single bonds. So you just have to know that this is the stable molecule. Now what's my AX formula?
AX3.
AX3. So what's the type of hybridization?
Triangle.
Type of hybridization?
Oh, SP2.
SP2, because it has to add up to 3. And then it's trigonal planar. Okay? There's no A in that, so everybody tries to say that it's triagonal, but it's trigonal planar. Are we all good with this? Draw the Lewis dot structure. Determine the shape all from your AX formula. All right. Moving on. Why is the shape important? The shape is important because it's going to affect the properties of the molecule. Now, before I get into even all of the polar and non-polar stuff, have y'all ever heard about a saturated fat versus an unsaturated fats in foods? Okay? A fat is going to equal a solid at room temperature, which means that the molecules attract to one another pretty strongly. So at room temperature, they're stuck together, they're a solid. Oils are the exact same kind of structure, hydrocarbons, but they tend to be liquids at room temperature. That's the only difference between the two. Is a fat is a solid, an oil is a liquid. They're both long hydrocarbon chains. Now, one of the big, one of the problem is we have saturated fats, and so when we have a long hydrocarbon chain, it's going to look like this. Or if we looked at it, it's going to look something like this. Each carbon's got 4 things attached to it, and so it's going to end up being tetrahedral around each carbon. Need one more hydrogen right here. And it's going to end up looking like this. So even though it's kind of zigzagged, if we go 15, 20 carbons long, it's really going to be pretty linear. So it's saturated. If a sponge is saturated, what does that mean?
It's wet.
It's wet, but what about how wet is it?
Like soaked in it.
It's as wet as it can get, right? If it's saturated, it's as wet as it can get. If this is saturated, what they're talking about is saturated with hydrogens. We can't add any more hydrogens to this. It's a saturated fat. They tend to be linear, which means they tend to stack on top of one another, and they tend to collect in your arteries, block your arteries, cause heart attacks and strokes. Now, saturated fats taste the best. They have a higher cooking temperature than an unsaturated fat, which means that you can cook your fried chicken faster. It gets crispy on the outside, not oily on the inside, and they just taste better, and they have a longer shelf life. So there's a lot of advantages, but the biggest one is they just taste better. So now with foods, we make unsaturated. Now unsaturated is simply this is a saturated fat. And unsaturated is going to have some double bonds in it. Oops. Hydrogen, 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 hydrogen. Okay? We could hydrogenate this molecule. We could add hydrogen gas to it, and we could break the double bonds and add more hydrogens. Anywhere there's a double bond, I could put a hydrogen here and a hydrogen here. I could put another hydrogen right there, put 2 more right here. So it's unsaturated in terms of hydrogens. Now, when we look at the shape of this one, there are 2 ways in which a molecule can grow around the double bond. So if we have the double bond here, if the carbon comes off on the same side, and this is hydrogen, hydrogen, we call this the cis isomer. Okay? Cis meaning same. The cis isomer. It's a cis unsaturated fat. On the other hand, if we have the double bond on the opposite sides, like this, just a little change in the structure, these are all hydrogens coming off of here. Hydrogen, hydrogen, hydrogen. But now, this is called the trans, like the transcontinental railroad, across. It's going across the double bond. If we have a cis isomer, it's going to have lots of bends. This is a cis. This has all the double bonds are cis in this one. And so as a result, it bends. It's no longer linear. Doesn't stack on top of one another as well. And so it's not more healthy, it's less bad for you than saturated because it's no longer linear. It doesn't collect. They don't attract to each other as much, and that's why it's an oil and not a solid at room temperature. So we have unsaturated. But if I have trans instead of cis, you can see from the drawing, it's going to be a lot more linear. Okay, so there's the double bonds going up, going down, double bond. This one switches with this one. And then we're here like this. Now you can kind of see that once again we're getting way more linear with our molecule when we do a bunch of trans. So you hear about trans fats. Trans fats are unsaturated, so supposedly they were good for you, but if it's in this trans form, if the carbon's going across the double bond, it straightens the chain out, makes it linear just like a saturated fat, which means it's just as bad. So in the 50s and 60s, they started learning more about heart attacks and cholesterol and all of that, and so they said, hey, we need to make too much butter, we need to make a substitute, make margarine. It's going to be polyunsaturated. It's going to have a bunch of double bonds in it. So everybody said, oh, we got to eat margarine. It's better for you. But then they started learning, oh, wait, the structure, when we're making margarine, it's making these trans fats instead of, the bent goods fats. And so now it's saying, okay, well, margarine probably isn't all that good for you. So you probably ought to eat the butter just in moderation because at least it's natural. So it's just kind of a back and forth always with that. But the point is that the structure makes a big difference. Nature has picked certain forms. When you put sugar, grow sugar cane, and you get the sugar from sugar cane, if you dissolve that sugar into water, and then you pass light through it, it actually causes light to rotate just a little bit to the right. So all the lights lined up, you send light through like a picket fence and you just have these beams that are all plain polarized. It'll cause it to bend. It's called right-handed sugar because it makes it light bend to the right. Well, all sugar that grows is right-handed, but there's actually a mirror image, just like the right hand is to the left. There's a mirror image form of sugar, of sucrose, that everything's the same. It's just a mirror image, but our body can't digest it. It's totally non-digestible. It tastes just like sugar, but it's 0 calories. Now the problem is that nature won't grow it, so you have to make it, and it's real expensive to make, and so it's not an economical sweetener. But the body again, the insulin that you take if you're a diabetic, it's left-handed. If you take right-handed, whatever the name of the compound is, insulin, but it's got a real chemical name. If you take the right-handed version of it, it's toxic to your body. So the shape of the molecule is super important as far as its characteristics. So we're kind of going in steps here to get into the real point, is that we're going from, okay, it's still recording, right? Because I think I forgot to put it on Do Not Disturb, so as long as nobody texts me.
So,
Okay. We're learning the Lewis dot structure, so then we can determine the shape from it. Once we get the shape, we can determine some of the properties of the molecule, which then explain why the molecules behave the way they do. Okay? So, we say the Earth has a north and a south pole. What does that mean?
like where it's like a magnetic north and like where the
Magnetic north, I mean, it's kind of like a magnet has a north pole and a south pole, a positive end and a negative end, right? But the Earth itself is neutral, it just kind of has a positive and negative end. Molecules can be polar. bonds can be polar. And let me just try to make sure I'm consistent with the notes here. So you probably want to get your notes out if you don't have them out. Now I'm going to be starting on Roman numeral 4, it's like page 4 or 5. Roman numeral 4, polar bonds and polar molecules. You can fill in all the shapes, like I'm just looking at D at the top of the page. Possible shapes of molecules that contain one double bond. Okay, if there are 2 single bonds and 1 double bond, that's going to be an AX3. With 0 lone pair, the shape is going to be trigonal planar. Okay, so we just kind of know those. You can figure that out from the sheet that you have. So polar bonds. I'm not going to follow the outline specifically, but what do you think a polar bond would be?
We're like everything's on one side.
Everything meaning?
Like all the like
What part of the atom is involved in bonding?
electrons.
The electrons. So the electrons, a covalent bond is a sharing of electrons. Now, I don't know if you have a younger brother or sister, or if you are the younger brother or sister, but I'm the youngest in my family of 5, and I was, quote, the baby. I got whatever I wanted, okay? And so I got more of the lion's share. I got, you know, my brothers and sisters had to share with me because I was the youngest. And so sometimes in a family, when you have to share things, is not necessarily sharing equally. So if you have to, usually if you share a car, the older brother or sister gets the more use of the car than the younger one. You guys may fight through that coming up soon in your life. Okay, so a polar bond, okay, it's an uneven sharing of electrons. Okay, an uneven sharing of electrons. We use the difference in electronegativities to determine the type of bond. Okay, so we're going to let X equal the difference in electronegativity. And I don't like to write this word out, so I'm going to abbreviate it after I write it this one time. From now on, I'm just going to say EN, electronegativity. Does anybody remember what electronegativity is?
How willing it is to lose or gain electrons?
No, it's more oxidation state. And I'm just using dots and X's just to differentiate the source of the electrons. The covalent bond is the sharing of this pair of electrons. The electronegativity, and again, that sharing means that this electron is drawn to this nucleus, this one is also drawn to that nucleus, and so since they're both drawn to each nucleus, they're kind of trapped in between. Okay? But it's a pull of war, a tug of war on here as far as where the electrons are going to go. Which one's pulling more strongly? Well, if it's chlorine and chlorine, the pull is exactly equal. And the electrons stay right here in the middle. They don't go anywhere. We have what's called a non-polar bond. It's an even sharing. Okay, so a non-polar bond, even sharing of electrons. Okay? So if I take hydrogen with its 1 electron and chlorine with its 7, now chlorine, and these values, we learned about the trends, but they're the values given on the back side of the periodic table that you have, the color periodic table. It's in tables in the book. You can always look this up. But chlorine's electronegativity is 3.16. It's a scale from 0 to 4 for electronegativity. This being strong, this being weak. So if we're looking at HCl, hydrogen's electronegativity is only 2.20. That means that chlorine has a much greater attraction for this shared pair of electrons than the hydrogen does. Which means that the electron cloud is not going to be evenly distributed. The electron cloud is going to be much heavier over here on the chlorine side than it is on the hydrogen side. And what's the charge on an electron? So we would say that this is a negative and a positive. We use this delta sign. This means partial. It's not a complete transfer. Chlorine's not strong enough to completely take the electron away from hydrogen, but it can definitely hog it. So a nonpolar bond is a perfect sharing of electrons. A polar bond is when there's an uneven sharing of electrons. And we can use the scale that's there in your notes. If X is less than 0.4, we're going to say it's nonpolar. If the difference in electronegativities is less than 0.4, they're about the same strength, that means the electrons are going to stay pretty much in the middle. It's going to be a nonpolar bond. A symmetrical distribution of electrons. If it's between 0.4 and 1.7, what's this one going to be? What's the difference in electronegativity? Is going to equal what? 3.16 minus 2.20, 0.96.
No.
0.96. It takes 80 to get to 3, plus another 16.
Sorry.
Right? So that falls, if you look at that scale, that falls in between the 0.4 and the 1.7. Now, if the difference in electronegativity is greater than 1.7, then we say one is so much stronger than the other, it just takes the electron away. That's going to be your ionic bond. Now, when we look up here at the periodic table, where are my most highly electronegative elements? Top right. Fluorine's the most highly electronegative. It's 3.98 or 4. Oxygen is 3.44. Some books say 3.5. Chlorine's 3.16. Nitrogen's 3.04. And all those values are given on the back side of your periodic table. So these top right are my highest electronegative elements. Halogens as a family are the most electronegative. Electronegativity increases left to right. Decreases going down, which means that these over here are your weakest. Okay? So if I take a metal with low electronegativities with a non-metal high electronegativities, what does that mean about my difference? It's going to be more. It's going to be big. It's going to be greater than 1.7 almost always. And so we have an ionic bond. So when you have a big difference in electronegativity, we call it a transfer of electrons. It's going to be an ionic bond. All right? So we have different levels. We have a perfect sharing. We have an uneven sharing where the electrons are drawn more to one or the other but not completely taken away. And then we have an ionic where it's a complete transfer when it's a big difference in electronegativities. Okay? Now, we don't really want to know, how am I doing? Is that pointed pretty close?
It says low battery though.
What? Low battery?
It made the screen blurry because it says low battery.
Just do that. Close. Continue. Okay. Only have a few minutes left. The camera's got to make it. So, polar bonds. Uneven sharing. Again, we don't want to have to look at all these electronegativities every time. So I'm going to give you an acronym. Okay? We're going to look at, we're going to call it phone call. Okay? F-O-N-C-L, phone call. If a fluorine, oxygen, nitrogen, or chlorine are involved in bonding, more than likely it's going to be a polar bond. Those are your most electronegative elements. They don't share well. They hog the electrons. So rather than going through and measuring out the difference in electronegativity on every bond, trying to decide if it's polar or nonpolar, we can just use these big four. If these are present, you can pretty much be sure there's polar bonds present. Okay? There are polar bonds present. Phone call. If that phone call is not involved, if there's just, sulfur and selenium and bromine or whatever, they're pretty close. They're going to have a little difference in electronegativities. They're probably going to be nonpolar bonds. Okay, now metal and a nonmetal is going to be an ionic bond. We know that. Any metal, any nonmetal, we're just going to call ionic. So we can determine polar bonds just by doing this. But now this is where the shape comes in. Just because it has polar bonds, the molecule itself doesn't necessarily have to be polar. Polar molecules, in order for a molecule to be polar, polar molecules must, number one, contain at least one polar bond. That's why we just learned what we did. And this is where we look for a phone call. Now it's really fluorine, oxygen, nitrogen, or chlorine. It's not, you don't have to have all of them, you just have to have any one of them present. Okay? But here's the key thing too, is the molecule must be asymmetrically shaped. It must be asymmetrical. Now, it's very important here. When you spell the word asymmetrical, there's only one S in it. A lot of people want to spell that A-S-S-Y-M. You don't want to be an ass when you spell asymmetrical. It's only one S. Okay? Thank you. I see a grin underneath that mask over there. Okay? But when you spell it, it's just kind of a pet peeve of mine. Spell asymmetrical with one S. Now, what does that mean, asymmetrically shaped?
Like one side's way different, or not way, just different.
It's just different. They're not the same all the way around, okay? Now, most of the time, we can identify an asymmetrically shaped molecule if it has a lone pair on the central atom. Now, it's not the lone pair that makes it polar. It's because it has a lone pair, it's going to be asymmetrically shaped. There are two exceptions to that. AX4E2, this square planar one. Do I not have it anymore? Did I decompose it? Oh, it's right here. This square planar one, this one is got two lone pair, but it's still symmetrical. That's just an exception to when it's got lone pair. Okay, and the other one is AX3E2. Pardon me, AX2E3. Like I3 minus. Okay, when you look at AX2E3, it's going to be linear. So those are two. You got to be on camera.
Sorry.
You're going to have two exceptions to our rule, but generally speaking, if there's an electron on the a lone pair of electrons on the central atom, it's going to be an asymmetrical shape. And we're going to look at these, and we're going to go back through all these Lewis dot structures tomorrow and look at classifying them as polar or nonpolar. Now, if the central atom has at least one lone pair, the shape is generally asymmetrical. But there are two exceptions. Two exceptions. Okay? AX2E3 and AX4E2. Two expanded octets, but they're symmetrical. They have lone pair, but they're still symmetrical. But generally, if it has lone pair on it, it's asymmetrical. You just have to know these. Just gotta pay attention to those. Now, got enough time, I think. The second thing here, if there are no lone pair, I say I move the camera so they can see this clearly. If there are no lone pair on the central atom, but all of the bonding atoms are not the same. Okay, that's your X's. You have different X's. The molecule is asymmetrical. So even if it doesn't have any lone pair, if the atoms aren't all the same, it can be asymmetrical. For example, CCl4. There are no lone pair on the central atom. This is a symmetrical molecule. If it's symmetrical, it's automatically nonpolar. You must meet both of these criteria. This is an and, not an or. Both of these criteria have to be met. So if it's symmetrical, we automatically know, even though it's got a polar, it's got phone call in, it's got 4 polar bonds, they're all going to pull in opposite directions and cancel each other out. The electrons are going to pretty much stay where they're supposed to be. But if I just change that up, even if I draw it like this where it still looks symmetrical, it's not going to be. Because now, I'm going to have a molecule that's going to look like this. We're drawing it in 2 dimensions. It looks symmetrical, but the reality is it's a tetrahedron. So the chlorines are pulling the electrons this way and that way, and there's nothing really to balance those out. So it's asymmetrical polar molecule. We're going to practice those tomorrow in class, okay? And just kind of go through that worksheet and figure out what we're going to do, okay? Oh.